Good morning. Uh, just to clarify, first, I'm recording this again. I'll put it somewhere online if you don't want to be in the recording, or if you're online. I've noticed actually records who is online. Just tell me. I'll try to cut it off. One thing that Ben and I talked about this on about variational autoencoders. When was it? On Wednesday? On Wednesday, one thing somebody mentioned and what was correct, they said you showed all this formulas, and suddenly here it started appearing like I don't know, pi, suddenly sigma. At some point in your code you had like Neperian E. Where these came from, and you never explained it. Obviously I assume these are Gaussian distributions, and a Gaussian distribution is what is it? I sigma 2 of e power 1 minus 2 x minus mu divided by sigma whole power 2. That pi and all that came from it. Is that clear? I suddenly I had like a leap of magic. And I didn't say where the pi came from, where they in the code. If you looked at it, there was a like E. I never explained where this E comes from, where the pi comes from. Obviously, all those probabilities are Gaussian probabilities. And I showed a single variant for multivariate Gaussian. You're going to replace mu with a vector of mu's, and you're going to replace a sigma with your covariance metrics. Is that clear? Just a clarification. I know that I jumped several oops there, but my I was trying to just clarify some of the basic concepts, but I didn't go through all the linear algebraic calculations for that, just to clarify. Today's topic is diffusion models. If you remember, if you have followed the trends of AI, something around, I think around 7-10 years ago, there was everywhere big news. Researchers at Google have trained them, giving lots of images to an AI, and their images have been cat images, and AI has learned to draw a cat. AI thought, I don't know how many of you came across that news. It was a few years ago. It was in the news. It was the big thing, like AI. Researchers have given, I don't know, thousands, millions of images of cat or videos of cat to an AI, and AI, by looking at it completely on its own, has learned to draw a cat. Now it looks like a caricature now. We have AIs can generate and if you would have seen the cat was not actually that great. Now you can generate AI can generate everything like and assuming you have given it sufficient detail. And this was the sort of early years of generative models. One of the most amazing generative models recently have become very popular is our diffusion models. And today is the last part of the series. I'm looking at generative AI. I'll cover the diffusion models. Again, occasionally you might see in your LinkedIn or in your social media feed, somebody puts an old image of very like some from, I don't know, late 1800 or early 1900 black and white image, or very sort of scruffy image, and they say, oh, we gave it to an AI, and suddenly you get this high contrast, high quality image constructed from that. By end of today, you will see how what is the mechanism behind those models, what actually makes the models to work on that. Before I go into the nitty-gritty details of it, I'll just tell a very simple story of it, how it works, and I think the rest will be just a bunch of calculations. In principle, the diffusion models mainly used for images. Take an image, and then at each step, there's an image, whatever is written, a bunch of things are in the image. Take this and add a little noise into this, and change all these pixels with a little noise. And they keep repeating this. At each step, they keep adding a little noise, a little noise, a little noise, add this, and they repeat it for many, many, many steps. When you get to a lot of steps, your image will changes to noise, becomes completely Gaussian noise. Like the original paper of diffusion model took 1,000 steps. 1,000 steps. Took an image, added a little bit noise, just a bit of noise. And the next step took the noisy one, added a little bit noise, and carried on, carried on. If you carry that, if you carry long enough and your steps are large enough, and you're familiar with all the Gaussian distributions and the Gaussian models, you'll assume you're going to tend towards a Gaussian model. And then you keep all these steps. You keep all these steps. And what you do, you're assuming if I could follow the journey of one single pixel through all these steps, this pixel was here, then turned to something like this, and later became like this, and it ended up like this. You just follow the journey of one pixel. And you see through these steps how your pixel kept changing in your space. Imagine this was your y and x. X were the time steps, and y was the sort of the value for each pixel. You're just following the journey of each pixel. And what happens is you say, well, if I know the forward journey, and if I kept following it, can I also learn the reverse? Because I can learn the conditional probability. Given the pixel was here, I added the noise that ended up here. Then you're saying, giving a sort of T1, but first you start with PT1, and then you say, giving T1, what would have been in time step 2? Giving time step 1 and 2, what would have been time step 3? And then you basically, what you do in the forward process, you don't have any parameters. Interestingly, and in contrast to many deep neural network architectures, in the forward architecture of this, there is no parameter to learn. Your network doesn't learn anything. It just keeps adding nodes, keeps adding Gaussian nodes. And you turn any image, and if you go long enough, 1,000 steps, or I don't know, 5,000 steps, whatever you are taking, you will end up converting your data to nodes. The beauty of it is when it starts, you are telling, oh, can I create a neural network? Now I will start with this noise and goes back to my original image of 6 and 2, and I don't know, something like this. Can I learn the reverse process? And the whole effort is, well, learning, imagine if you took one of these pixels and you tried to directly predict it from here to here. You said, well, you know what I do? I'll take one pixel, and if a Gaussian noise, I'll just use a Gaussian prediction to say what would have been here, right? The problem is your margin of error is very high because this image has changed in 1,000 steps. You're trying to predict it with one Gaussian noise, your margin of error will be very high. But if you have added this incrementally, just a little noisy, just a little noisy, just a little noisy, from one step to the other, your sort of margin of error is not that large. In reality, what you do, if you had a high quality image and you had just one little lower quality, it's very relatively easier to learn to get with a little lower quality to your high quality. It's very easier to learn. And in each step, you train the model to go just one step. So just learn for the one step. But incrementally, you do one step. Each model just learns taking the previous one and improving it a little. The next one takes it and improves it a little, and improves it a little. Interestingly, if you put it all together, suddenly you do a large task. Imagine if you were going to remember, I don't know, an entire book. For each of us would have been difficult. But if we had 1,000 people, we ask everybody to learn 5 words, and I tell you the 5 words, I pass it on to you. You add another 5 words, you add another 5 words. Probably in like a matter of like 3 minutes, we can learn like I don't know, a 50 pages book, right? It's the same concept. If I could just let them incrementally help each other to do that, that's the entire diffusion model. With the hindsight, I don't know why any of us didn't think about it, but somebody came up with the idea, and the rest is just a little bad bit of math. But in reality, you see, you're going to learn conditional probabilities. And in reality, if you look at how image processing and models of learning, like, for example, to improve the images or do predictions, or if you have done like a lot of Gauss conditional probabilities, conditional Gaussian models, in reality, it shouldn't be that complicated because we can just take one and condition to the one we predict the other. And because each time we have just added one level of Gaussian noise, our margin of error will be smaller and smaller. Like we are not going to make suddenly 1,000 steps up. And amazingly, the end product of you, if you do it long enough, is noise. And then what then looks like a leap of magic, if you learn the reverse process, now you're going to give noise, and your model is going to create a high quality image, which with all these things, and we will see when we cover the math and how this works, but still, when I look at the end products of it, it still seems to be magic. Like you just give noise, and suddenly your model generates these sophisticated images. And then just telling now to create from noise, create a cat or create a dog or create a cat swimming in the sky or whatever, it just you condition it to text. Means when you are giving the images, you say this image is cat. Then you learn the parameters conditioned to a textual, a series of text basically labels. It's just an extra layer of learning. You're just conditioning it. But for now, imagine you just learn it. Interestingly, when you follow the journey of each pixel, one thing I didn't say in my explanation, you're not following the journey of a pixel on its own. You're following also the journey of a pixel in relation to all other pixels in the image, because you are taking a multivariate Gaussian. In multivariate Gaussian, your predictions, whatever you're predicting is sort of multivariate distribution. It means every single dimension is not just on its own, also has dependencies to other dimensions, which is the mu covariance and mu's across them. Make sense? That's all. That's how diffusion model works. In reality, now in mathematical terms, you're giving just a sample. You take a sample data X and you go through an intermediate latent space. Basically, each of your time steps, it takes like generates a latent representation of it, and you carry it in large enough, sort of. To get to a Gaussian noise, and then you repeat it. And both encoder and decoder mappings are stochastic rather than deterministic. You're just basically adding, probably stochastically, you're just adding noise to your data. If you look at the generations of how the generative models worked, a big sort of push in generative models started with GAN, generative adversarial networks. When in reality, what you were doing, you were training your model to recognize cats. And at the same time, you had another tier in your model, which you were starting with a Gaussian noise. And this part of the model, which was sort of the generator, had a discriminator. And the discriminator looked at basically detected this image is a cat. And each time you gave your noise generated image and you looked at, if discriminator detected this is not a cat, this is not true, you rejected it and you kept updating your network. And you're basically the part of your network which was taking out noise, Gaussian noise, and was generating these images of the cat, it gradually you improved it until actually you could fool your discriminator. Your discriminator couldn't distinguish this was a synthetically generated. Once you could fool your discriminator, you were saying, okay, my network now converges to create a cat image. And then just to avoid creating just one good cat image, then GANs, they have different techniques and add noise and things to be able to create variety of samples in that category. Then variation autoencoders, I talked about them on Wednesday, and you see that they are using a probabilistic way of learning it. There's a bunch of models, they call it flow-based models, which they are trying to learn a function. Basically, you're assuming your data, you can convert your data based on a function to a series of latent representations and use deep neural networks to learn a reverse function to be able to do that. In reality, diffusion models, they just take that and do it step by step. What they do is step by step, they take X0, which is your original data, add a little noise, a little noise, a little noise, and they repeat it many times. They get to Z, and then try to, in the training, they try to learn the reverse process. In fact, you have the images in the forward process. You have all the, let's say, you've taken 1,000 steps, you have all the 1,000 intermediately generated steps. And what you do, each of those, you have added Gaussian noise, and you just try to, based on many samples, many iterations, you're trying to learn, if my sample went from A to B, T1 to T2, can I predict the mu and sigma of the noise basically added to that? I'll talk about the sort of predicting mu's and sigmas, but actually the practical diffusion models, they don't try to predict the mu and sigmas, they just predict the noise added to the image. They just look at
can I ask a question, please?
Sorry?
Can I ask a question, please?
Sure.
I didn't quite get in what circumstance one might want to use, let's say, a variational kind of encoder, and in what circumstance you might want to use a diffusion model, because they both seem to kind of identify these latent kind of variables and then generate, I don't know, your image that you want at the end. I mean, how do they compare, and what circumstances would you use one over the other?
That's a good question. Part of them are just sort of incremental, different approaches for generative models. Part of it is just that been designed and created over the years. part of it also, if you look at in variational autoencoders, you get your Z representations. These Z representations are your latent variables. For example, you can use this as your feature encoding model. And your feature encoder model also take the social sort of the spatial relationship, for example, an image and learns them. Then while you can also use it as generative model, you can also use this as sort of a feature representation, later feature representation. And because it's also, you have this Z representations, you can also control a sort of what type of end product. I'm trying not to use always images. That Z can be anything, but you can control what type of images you can create. Basically, you can manipulate some of your Zs, and the rest of them, let's start with sort of a Gaussian noise, right? You can say, if I had like my Z5 features, 1 and 2, I want to exactly move with this, you can control them or you can limit them, and you can say the rest of them take a Gaussian noise. If you see in diffusion models, your control is a little less, because your model is basically a hierarchical model, a step-by-step adds noise and takes it back. You don't have like a sort of a layer. You say, okay, I take layer not 500, and this would be my latent representation. Here, you don't have as such a latent representation. Depending on application, if you're only you want to use to create, let's say, high-quality images, you would just look at which one performs best, which one gives you the best performance. And diffusion models, often they are, if you look at against the benchmarks, they're one of the high performing ones, with some caveats. I'll get to that. But in reality, sometimes it's not just creating the high quality image. Sometimes you are interested in the sort of the side product of it. For example, as I said, in semi-supervised learning, you have a lot of unlabeled data. You're not really interested in maybe the generative part. You're interested in the encoder part of it, because you want to give all this data, and your model learns the latent representation of that data. And you might train a variational autoencoder, and in reality, you might just not use the decoder. That's, for example, what Nan is doing for her PhD research. She's creating a convolutional variational autoencoder. But in reality, what she's interested is in the encoder part, because we have much smaller subset of label data. And if we could train a sort of an auto-generative model to learn how our data gets correlated in a latent space, we can use those with a smaller data set to create more robust classifier. Did I explain, Fatima?
Yes,
Did that
thank
answer
you.
your
That makes
question?
yes, thank you.
But generally, but the most application I have seen for diffusion models are in images, and generating basically images conditioned to a text, or a condition like just to start with noise and generate images. And in reality, people use, for example, look at in your Photoshop, you have a clip art which uses stock images, right? And if you had a diffusion model now, rather than using stock images, in reality, maybe in a few years, you just say what you want, and a clip art generator will generate that for you. And in reality, this is already happening. And when diffusion models were introduced, they were the best performing models in creating these generative models. Interestingly, the work itself, the original work, which most of my explanation will rely on, didn't come from Google Research, but people at Google Research took it and improved it, and they made something really, really interesting from that. Again, just quickly, like Roxandra for her MSc project, she's taking EEG images, sorry, EEG is not image, EEG data, and creates images from EEG, which there you can use some computational techniques, but literally takes the multi-channel EEG, represents it as an image, and then trains based on just thousands of images she has, trains sort of a diffusion model, which learns how a seizure EEG will look like and how a normal EEG will look like. And in generative model, now you have an in silico model of a synthetic model. You can just basically constantly generate your seizure brain EEG data. It can create your healthy brain data. Now, just another dimension to your question, Fatima, like we were trying to see now, can we simulate the effect of, for example, DBS, deep brain stimulation, in these generative models? If you do that in diffusion model, but by the end of hopefully today, you will see your diffusion model, whatever you manipulate your inputs, probably will ignore it. We'll see it as because it's just denoises, and we'll see that the denoise. And then we realize, oh, that's going to become much more complicated. There are techniques to do that. You can inject something, residual nodes and things, and it becomes much more complicated, because in the reverse process, your model constantly tries to denoise your data. But if you take, for example, a variational autoencoder, and you take the variational sort of latent space, you might have better control. That's my intuition into it. Anesthesia's question is, in reality, what you do, you take an image, you take an MRI image in 1000 stage. Basically, you keep adding, and your stage 1000 is noise. It's pure noise. Now, how are you going to reverse it? How are you going to reverse that problem? Yeah, you're not interested in the intermediary ones in such. You're interested in the end product. The only thing you're trying here to do, or the main thing you're trying to do here, is can I take now a noise and generate my original image or series of my original images? It's more like, I'm guessing, That's correct. Oh, the question is, if you have 1000 MRI images or 1000 CAT images or whatever, how you integrate all that. If you had one sample, you probability training, you're training your probabilities with one sample. I mean, in probability theory, your probability is not reliable. The more samples you have, you're constantly going to train and improve your probabilities. Right? The more samples you have, and these techniques, they use thousands and millions of data and computation. That's also the race in AI now, is the more computation power you have. And in reality, even simple Oscar Sandra, even the simple diffusion models, they need GPU. Can't even train it. I mean, you might be able to train, but you have to be really, really patient and have a proper coffee machine to sit for like 2 days to just drink coffee and watch to get training. They need high computational power. But in reality, what you do, you constantly feed data and you improve your probabilities. If you give one image, what you reconstruct will be terribly bad because you had just one sample to run these probabilities. The next one will be better. The next one will be better. And if you see how the deep neural network work, you make your data into batches. You give the batch data, you measure your error, retrain it, and then you give all your samples for when you give to the model. You call it one epoch. Means your model has seen all the samples once, and you start again. And sometimes you train these models for like, I don't know, 30, 100 epochs. And imagine if you had like, I don't know, 50,000 images, 50,000 times multiplied by, I don't know, 100 epochs. There you go, how many times your model has seen this and constantly has improved itself. Imagine if you had a process to be able to create a stable learning process out of this. You're assuming your model keeps converging. Now, amazingly, you really literally, you give Gaussian noise. The starting point for this will be Gaussian noise, but an image, a model has learned place of every single, means every single pixel will be generated randomly. And the leap of magic is here. You will take that random and your model has learned to multiply it by certain weights at each stage, conditioned to the other pixels' random values, and generate a slightly better looking. And I'll show some examples. And you follow that journey 1000 steps. And what you have learned, your model has learned from step one before to the next, one before to the next. Then at each step, not trying to make a massive guess. It's just trying to see what could be the next one based on what I have seen, based on what I have seen. And the amazing thing is, if you break this problem to a very, very large problem, and if you're familiar with like how the Gaussian models work, in theory, you think, well, I can see how it works, but it's amazing it works. Does that make sense? You will see more examples of that. This is slide basically just explain what I said. In reality, what you do, you first start giving X, and you're conditioning each of these intermediary steps to this QZ. And also, by the way, it's amazing where we started this module. Like the very first days of when I started in January, I had to define what a probability is, what a conditional probability is, and now you're becoming so some of the things so complex. Even myself, I struggle to follow. And my feeling is, I think this is more than probably you would have gotten a computer science course, but us have tried to keep it like sort of manageable. I hope it's useful. That's again is a very good question. And the question is, do you really need to push it so far you make it complete noise, or there's the benefit you just stop somewhere and you start learning halfway through? A lot of just classic tutorials you see, and a lot of the initial generative models, the way they are designed for the applications they are designed, they really tend to push it to become the noise, because what they want to, they don't want to start with the Gaussian noise. They want to start with the Gaussian noise conditioned to a text. then you say like cat and sky, and the condition that Gaussian noise generation to that, and then take it from there and sort of improve it. That's the most dominant application you see for this. But if you take, for example, taking an old image and improving it, you may not need to go to the Gaussian noise. You say, this is the level I want to stop. And if you have a good sort of prior, that what level of noise you want to stop and be able to do. There are categories of this diffusion models which people use like for basically denoising it. There still can be pushed to the noise. The more imagine, the more noisy you make and the more noisy you get. Doesn't matter if you start with a better, rather than the Gaussian noise, if you start with a better representation, your assumption is model the live and make it better and better. And some of these images they create, and then go and look at it. And I have some examples here. It's just like mind-blowing. Like you really like, I find that this is quite amazing, that like the way they work. Like, but let's go through this example. You start with like a, say, image like this. This is your x0. This is your starting point. This is your first training. And imagine you have thousands and millions of this training data, and you go through these steps. And each step you add noise, a little noise. You see, for example, I don't know, this is step of 531. Your image will look like this. And when you get to step 1000, you become like completely like this. And you say, wait a minute, if I knew all these steps, and if I learned this conditional probabilities of xt minus 1, given extent t minus 1, which this one, and predict xt, can I just, because you have all the images, right? You have the image here and you have the image here. You say, given this, can I predict this? And imagine you're, in principle, if you look at like with one step, it's not a like super complex task. You have just one image. You have thousands of this, obviously. You're just taking with this and you're trying to predict this. Okay? And you have thousands and thousands of the samples to do this. In reality, if you look at it just for a single step, computation in terms of the training machine learning models doesn't seem to be a very complicated task. The beauty of it, it puts like thousands of steps of it. And the beauty of it is there is a sort of a guided now added Gaussian noise to original images, and you just reverse that process. Make sense? In principle, it's very simple. The math behind it, how you train it, how you calculate the loss, becomes a bit sort of maybe a little complicated and requires a little linear algebra, but it's very similar to how you train variational autoencoders. Another sort of additional answer to Fatima's question, in reality, diffusion models are hierarchical variational autoencoders. In reality, they just learn hierarchy of these models. But in reality, what you do, you're not just creating one image, you're also having classes of images, dogs, I don't know, cats, sky, and different things. Then you also have a text you add to this. Usually you have a sort of text and go through, you need to do the text embedding, you do the language, and then you condition learning this to the text. And a lot of diffusion models also, you see that they are looking at a diffusion model of like, for example, here you're using 2-scale images, like basically images from 2 different resolutions, and you learn diffusion models together. What I'm trying to say, the end products, what you see, for example, they generate from noise. Basically, this is actually a model. If I'm not mistaken, I took from Google Research. You just write something like this, a text. You want to that one. And the model has learned seeing all these keywords with a lot of like sample images. But in reality, also the model at each stage also might create different resolutions. Then part of your diffusion, maybe you just take like a smaller scale image and you create a better version of it. And then what happens is, if you cascade this diffusion models on top of each other, and imagine in the large language models we looked at, like how people stack these transformers each other, here is the same. And then you start creating a little smaller image. Then you take that and create a little bigger one, and then you suddenly you end up having a super high resolution image of a dog. And imagine this is literally generated by an AI. Scary, interesting, and mind-blowing. And in principle, with the hindsight, not that complicated, is it, Olivia? Olivia's question is, often when you train it, you're not just training for dogs or cats. You might have a large number of this vocabulary. because exactly the same complexity you're adding to large language models. In reality, you might not just have a diffusion, you have stacked models, more complex models. But let's simplify it or oversimplify it. What you're learning each time you're creating this diffusion and learning the parameters, you're conditioning it to the label you had given. And now you're adding more and labels. Basically, that becomes the more conditional probability. Given X and Y, given cat and dog, what would have been this? You're just adding more conditional probabilities to conditioning on different probabilities. As I said, the Ho et al., which they wrote the original paper for this, is they took 1,000 steps. And a lot of classic examples, you see they use 1,000 steps. There's nothing to stop you if you want to do 10,000 steps. Just be prepared for the computational complexity of it. And then you start with, in T0, you just start images. And as I said, step by step, you just add noise and then reverse it. And as I said, in reality, in your encoder, in contrast to, if you remember in variational autoencoders, you for example, in your encoder, you had the Q parameters, you had to learn the Q and theta. And in your decoder, you had this generative part, you had to learn the P and phi and all these parameters. Here in your forward process, when I say there is no parameter, doesn't mean doesn't have any hyperparameters. There's no hyperparameter to learn. And you will see there is nothing you need to have like a stochastic gradient descent or some loss function to learn. The forward process is straightforward. You add a bunch of, you will see a bunch of variables, and you will learn that what you are trying to learn are this reverse probabilities and reverse processes. Again, you take an input, and in Z1, Z2, at some point in ZT, let's say here is T equal to 1,000, you get here, and then up to here, you just have a bunch of parameters you added, and they are fixed, and you define them. And then the training part comes from you give this, and you learn. Given this one, you learn this. Given this one, you learn this. Given this one, you learn this. That's it. That's really how a diffusion model works. Now, how you add the noise, you're having these parameters of beta, and you define these betas, which they are between 0 and 1. I just highlighted here. Just use a more obvious color. You just is predetermined. You say for each of this t, and usually you might just make the beta changes like slightly at each step. You just define something like a decaying function. You define a decaying function. And also you're adding a ET, which is just the standard normal distribution here. This is standard normal distribution, like 0 and 1, like a Gaussian distribution. And you're taking it and you're adding sort of a little bit of a noise. And this is the formula. Basically, you take 1x and you multiply it by this plus, and you add it by square root of beta 1, and you add an epsilon. You see how you do? First, you scale it by square root of 1 minus beta, and beta is going to be a very, very small value. Then first you multiply your x by that, and you add it plus square root of beta 1 and plus that. And then you go 1 minus beta t, and you carry on. In each of them, you slightly change. And beta 1, beta 2, beta 0, beta 3, all of them you can trace it back, because you start from a value and you change the beta from slightly. Does this make sense? What happens is, if you take each of these pixels, each of this here on the x-axis are pixels and an image, and you go through the z steps. Each time you apply those values, this changes. Like imagine again, look at this previous formula. You take x and you have to multiply this by this value, add it by this value, and this epsilon comes from a Gaussian distribution. If you keep adding it, this is journey of like now 3 pixels in your image through 1,000 steps. Like this one starts from here and ends up here. This one starts from here and here, and each step you're basically looking at the distribution you are drawing from it. Make sense? And what you're trying to learn in your reverse process, you are trying to learn these distributions. You're trying to learn, if I were here at this stage, I don't know what stage is here, what distribution will represent it. You are trying to learn mu and sigmas at each step, what distribution will represent that. And imagine if you have thousands and millions of samples, for every single pixel, you're going to learn in Z40, my distribution, which represents this pixel, sits here. And in reality, you learn all of them together as a multivariate Gaussian. Does this make sense? The only thing now we need to find out how to train that problem, how we learn those probability distributions. We know now we can find the probability distributions. We know if we find the probability distributions at each stage, we can predict, and we can becomes a conditional probability, becomes a conditional Gaussian multivariate Gaussian. The only thing now we were going to struggle a little bit, but there's a way, is how to learn these probabilities, how to train based on all this data we have. Before doing that, because we are applying it in a large number of steps, like if you are doing like 1,000 steps, you don't need also to wait like each time sequentially to wait to generate it. In reality, you can actually generate all the 1,000 steps one at the same time. And I'll show you what happens is. But in reality, what you're trying to learn in your decoder is just, as I said, the conditional probabilities. And you're assuming at each step when you're doing the forward process, in forward process, you're just taking a normal distribution of basically this is the mu and this is the sigma based on the betas. You're assuming that each step your data comes from a sort of a Gaussian distribution which you're adding noise to your data. And in reality, you say x, giving x, this steps are, for each step you can calculate this. Basically, it's just writing it the same mathematical form. At each step, it depends on the previous steps, just the same thing. And the step one, obviously, is just giving x. The step others, they are depending on z's. Is that clear? Just the same thing I've been showing, just writing in a little more mathematical format. And imagine if this is like your x's and going through this. Again, this is the same concept, showing it across like sort of your x starts from here, and basically at different steps, because this is a probabilistic space, like it doesn't mean the next time you draw it, you might just take another one, you might take another one, and your x can take multiple journeys, like your x1 through this 1,000 steps, because you're adding sort of, when you're learning the reverse process, the conditional probabilities. Now, and this is the area your x could cover. The important thing is, over time, you're going to learn and converge to be able to better predict better what that pixel will be at the next step, rather than, obviously, if this becomes very wide, your margin of error is going to be bigger. You're trying to make better and better predicting the reverse process. Or in reality, what you're trying to do, you're trying to find a marginal distribution. Giving each of the steps before, you're trying to predict what is going to be the next step. This is a marginal sort of probability. Condition to the previous one, what is going to be the next step. And for each of them, what is the probability of sort of one of the pixels being, I don't know, in certain areas, and you're going to learn this conditional probabilities. Now, when we apply the sort of the forward process, we are creating basically a diffusion kernel. What we are doing, we are taking again each z takes basically x, and I'm just repeating the formulas, and adds a 1 minus square root of 1 minus beta plus sort of square root of beta multiplied by epsilon. So I said, now our effort is, do we really need to go one at a time to generate this 1,000 steps? Because in reality, if we have 1 million images, and for each image, we want to create all this 1,000 steps one by one, it's just a matter of we have to wait. Can we just take an image and create all the 1,000 steps at once in parallel? In reality, you can. And it's just shown here. I again took out Simon Prince's book. I've just shown what Z1 will look like, what Z2 will look like, and what is the relationship between if you just plug sort of this one into Z2, because sorry, each step depends on the other one. Just look at this formula and plug one into the other. You can just create, always based on the betas, the next step. You don't need to always create. You will need all the 1,000 samples, but you don't need to generate just one and wait and to generate the other. You can just plug them into each other in this formula, and you just generate. You say, you know what number 1,000 would have looked like, sort of starting from the point. And that basically helps you in computational efficiency, because you can just take and define an alpha t, which becomes your 1 minus beta, and you can plug it in the formula. Then you can generate each of the zt's conditioned to x. This is just to speed up the forward process. Does that make sense? it just was a little algebraic thing. You just plug all the variables previous one and just to do a bit of calculation. In reality, you will end up, if you created an alpha, it becomes 1 minus beta. You just can plug that. Or I think I have a representation of it at some point. I'll show you. I don't know where in my slides. Basically, you can write it in the mathematical form where it comes from. Makes sense? In reality, it's just the computational efficiency. Otherwise, if you're patient, just go on a step-by-step generator. Just wanted to do. Now, what you're trying to do for the reverse process, we are trying to learn the marginal distribution of Z, which is the probability of observing a ZT given the starting point of X and going through the diffusion process. Means ZT will depend on X and all the previous steps before that, right? It's conditional probability. Obviously, if you're looking at the previous one is depends on the previous one and goes on until depends on the X. And you're trying to, basically, this becomes your diffusion kernel. And in the decoder part, you're trying to learn the reverse process. Say, okay, if I looked at that and learned all these probabilities, can I just reverse the process? Basically, can I calculate this integral, looking at what was the probability of X happening in the first dx and giving that X having that ZT? If I can calculate this integral, I have my solution. Basically, I can find all the probabilities. Or if you write a conditional probability, you are saying condition to ZT, this is just a Bayesian, basic Bayesian. Giving ZT, what with the likelihood of probability of ZT1 would be this. Yeah, just a simple Bayesian rule. And in reality, what we are trying to do, we are trying to learn a bunch of conditional probabilities using a Bayesian representation. And in reality, what we are learning is a multivariate Gaussian. Again, repeating the same thing. And we are assuming, yeah, diffusion kernel are normally distributed because at each point we are adding Gaussian noise and we're drawing from the normal distribution. We are assuming our data is normally distributed. Now, if you plug this, and if you're saying this, and if you've seen this, we can always say this is proportional to this value, to this part, right? I mean, we do this in a lot of machine learning. We can say this is proportional. And if you just plug these values, ZT is just a normal distribution of 1 minus beta values of ZT minus 1, and the beta T at that point, and then multiply by a normal distribution of now ZT minus 1, which becomes basically you're using now the alphas. Yep. A little more algebra, just a little more algebra, just now sort of now divide all of them by sort of 1 minus beta and just carry on with a little more algebraic representation. You're conditioning giving X and ZT, you will add ZT minus 1 will be something like this. It would be a normal distribution of these parameters. And so far, now this is a normal distribution. This is our mu, and this is our sigma. Interesting, or depending if you're looking at multivariate distribution. Basically, this is what we are trying to learn. For each step, we are trying to learn a multivariate Gaussian, which is conditioned to these alphas and betas, and they will help us to learn the mu and sigma of that multivariate Gaussian. I'm not going to go through all the algebraic representation, but in reverse process, you're now looking at the samples. You are trying to train your model to be able to do that. Probability of ZT, the last step 1000, which we're going to start, in reality, you start with random noise. You're starting with the standard distribution. It means in the decoder, the first step you start, your starting point now is noise. And that noise is drawn from random distribution, normal distribution. And then what you're trying to do, you're trying to now learn this phi, the parameters for the conditional probabilities, similar to a variational autoencoder. The difference is, so far, I represented them as conditional probabilities, as Bayesian inference, but if you've done Bayesian inference, that looks horrendously complicated. How do you learn that Bayesian distributions? You might be able to learn it, but it's very, very difficult to train that. The beauty of deep neural network is you plug a neural network into it. And then provide a deep neural network to your decoder, and you teach your decoder to do it. And in variational autoencoders, you saw that. you can train a deep neural networks for that one typical function. And that's the link between, that line is the link between variational autoencoders and diffusion models. That's how diffusions, if you look at when I said hierarchical, basically now you have 1,000 of them. Each step they are learning the next one. Does it make sense? Okay, then I can pretend I'm explaining it, but I can skip some of the training parts because sort of in a very sloppy way, I covered it in variational autoencoder, but very similar. In the training phase, what you do, you're starting and you're saying, giving the phi are the parameters of your decoder, and giving Z1, you're trying to basically the end, you're trying to predict X, but this is conditioned to all the previous steps. Then you start with ZT, which comes from a normal distribution with mu and sigma of 0 and 1. You start with this and step by step multiply all that with the last one, which becomes just Z1 and this, and will produce X. And that will generate your probability of creating X. If you learn that probability, distribution, what you do in reality, you just draw a sample from that probability distribution. Amazingly, that might look like a dog if you have trained that probability on dogs. Makes sense? In reality, what you do, if you're giving a 1,000 by 1,000 MRI image, magically, but through a diffusion process, you have learned what the probability of every single pixel on that MRI will look like. And in reality, your model you can draw samples which will be very real looking. And each sample, each time you take one pixel, they will be conditioned to all other pixels, and you just draw samples. Make sense? And this, because it's repeated many, many times, and your model, as I said, the traditional ways of doing the sampling and everything and training these models would have been in Monte Carlo. I don't know, Markov chain Monte Carlo model, very complex models to train it. You basically delegate that task to a deep neural network. You learn a function to be able, you're learning a neural sort of function which is represented by a deep neural network. What you're trying to do, you're trying to maximize the log likelihood of this. Pxy, giving the parameters of phi, which represents the parameters you have learned for your reverse decoder network over its steps. And what you're trying to do, you're maximizing, giving these parameters, I get an xy. In reality, during the training phase, you're just creating, basically making your network to generate the image you had. Because you have given the image, you've generated the noise, now you're giving the noise you had created from that image, and you're just giving it back to the model to generate the image you had given. Then in the training phase, you're using pre-orchestrated samples. Your noise is already orchestrated because you have created the noise after 1,000 steps. Then rather than just drawing randomly, you just give that noise, and then pre-orchestrated way, you know what happens next. And you are training the model, take that journey back to generate the image you knew. And then you will measure the difference between what you created. And the first time you will do it, you will create a terribly bad image. And then you take the sort of the error of it and you plug it to the network and you repeat and repeat it. Very, very long iteration. But when I say very long iteration, maybe you have like 30 epochs. But imagine in each epoch, you might have like, I don't know, 10,000, 100,000 images. Yeah. Make sense? Goes to the beautiful part of the evidence lower bound. And as I said, mathematics, especially linear algebra as a subject, is badly represented. They are not as difficult as they look like. It's just a matter of if you're really interested in. I've provided the references. I think Simon Prince's book is your friend if you're interested in the linear algebraic sort of representation of it. And then Prince's book has really interesting references to more. If you're interested even more than that, you can go into it. But if you're looking at it in single weight, this is very, very complex. It's not as complex as it looks like. And you, in most cases, you might not need to go and learn everything about it. But I cover it first with the start, means you can always ignore and check your Twitter if you want. But also I'm covering it because understanding how these things work will give you better tools of making decisions where it could be useful, or if something happening or unexpectedly something generates results, what could have happened in the process, just knowing it. And often my own approach to these things is I'll learn the process, but I don't remember. If you ask me to write this down just from memory, I cannot. And what I, for myself, what to do, I try to understand how these things are designed and work. And if I needed it one day to really, really go and change something in the design, then I go and start in detail. What I'm trying to say, sometimes it's just superficially understanding how these models work is very, very useful. And as usual, I think if you leave this room and you think like 10% of the diffusion models, what I said, you could remember, dude, I think I've achieved more than actually what I hope will be useful. Anyways, going back to evidence lower bound, I covered it when I was talking about the variational autoencoders. You're taking the log probability of this. You're starting with basically conditions of this parameters conditioned to all the z's you have seen, and you are to generate the z. And then you're going to Jensen's inequality. If you remember, a g of a function you could type is always greater than or equal to of the function if you add the g inside. And exactly here we have done here. We've taken this log probability, we say equal or greater to, now the log has gone inside. Does that make sense? This comes from Jensen's inequality. If you're interested in what Jensen's inequality is and how it works, again, linear algebraic reference books are your friend, or there's a good entry in Wikipedia about it. And then this evidence lower bound, what's trying to do, you're trying to maximize this probability. You are trying to say, giving all the parameters of the phi of the network and giving all the steps divided by the evidence I've seen X and giving this parameters, I'm trying to maximize this basically and reduce the error. Basically, you're trying here to minimize your error. And I'll come to the cost function, how we define it. Now, to simplify it, this is actually simplification of what you had seen in the past. If it looks more complex, here just showing the steps. Basically, we've added that sign shows many times they are multiplied by each other. How many times they are going? This is like similar to sigma. Just this is here. Sigma is plus. This is a multiplication. And if you take that and then write it in that form, and then you separate it, because again we talked about it. Log of AB is equal to log A plus log B. And if you apply this here, you will get something like this. Yeah. Just do a bit of calculation, and then you can use that to, I'll show how you're going to use that to basically define your error function. If you take this now, this logs, and do a little more algebraic calculations, I forgot here again, similar to variational autoencoders, we introduced a parameter of q. We couldn't solve the because the integral was intractable, and we didn't know, we didn't know the z space. We introduced a new parameter, a new distribution q, and if you multiply it on both sides of the division, that they can even themselves out. But in reality, what we do, we take it out. And if I'm not covering it, you think long enough, I mentioned this in the previous one, please look at the recording. And if you take that, what happens is this is giving the first or the last decoder step. This is the last decoder step. Like if you took from the noise, this Z1 is just one before you create the original image. This is just one. This is Z1. And from Z1, you're moving to X. Then the likelihood is giving the parameters of this network with Z1 to create X condition plus all the log likelihood of others. Basically, there are a bunch of log likelihoods. The likelihood of you generating the last image is conditioned to all this. This makes sense. And then if you write it a little bit, do a little bit more linear algebra, you're creating something like this. Yep. And you will see this is now going to convert to a KL divergence, because there are two probabilities. You're trying to take the difference between two probabilities and add it to this one. Again, continue. You see my stars increasing. Just continue a little bit more linear algebra. Add this, and basically, this is the one part of this is the expectation of this. This is the expectation of X, giving X to find the Z1 minus the KL divergence. Basically, this is the KL divergence of these two probabilities. And we said the KL divergence is just how you calculate the distance between two probabilities. Right? And this will give you the evidence lower bound. And we said if you have the lower bound minus the lower bound, always will maximize the probability. In reality, use that lower bound to define your loss function. Your loss function, because once we have the loss, learning a neural network here, you're going to apply, for example, a stochastic gradient descent, and you're going to update the gradients. Means what you do in each step, you just update your models a little based on loss. You update your weights, and each time calculate the loss. In reality, your loss is the reconstruction term, what your network has generated. What I forgot to say, we keep the sigma usually fixed here. To make it easier, you see all our effort is focusing on defining the mu. We keep the sigma fixed for now. The standard deviation in these terms are fixed. And what we are trying to do, we are trying to learn this. The neural network parameters will give us the mu of the distribution, and condition to this mu of phi1 z1. This is this reconstruction loss. What you reconstructed, given this, plus mean of, given x and all zt's, you're taking the mean of each step, how much error you had in reconstructing each of them. And this is the basically predicted zt minus 1. Means condition to all these things, what you got as sort of zt mon in each steps, plus what you predicted as zt1. You reconstruction loss minus all the errors you had in between. You take the main part is here is once you had the before the last step, before actually you generate the image, you take that and you use that as reconstruction. You said condition to network parameters. If I had zt1, which is one before your original image, you say what was the reconstruction loss from that, and then you're basically what you're doing, you're adding the loss of everything also you had in between, and you take the mean of it. Make sense? You do a bit of reparameterization to just make the computationally easier. You define zt. We knew from the forward process zt is like this. We knew x can be calculated like this. You plug it in. Your basically your loss function becomes a bit simpler, because now you have the parameters, you have alpha and betas. And if you have an alpha and betas, you can plug that into the model and you calculate the loss. Now we have the value, we have the parameters, to calculate the loss in this one. And then we can use the loss to update the model. Again, like any other neural network, the process is like that. It's a very simple, typical neural networks. Your neural network generates a value, like generates a number. Let's say take a regression, and you know the exact value. You just calculate usually mean the squared error, and you use that as sort of a guide, or you calculate your gradients based on that, and you update your weights here. Because these models are much more complicated, it's not just simply how should I calculate what is my loss value here. And this evidence lower bound and all the processes I told you will give you a function to calculate the loss. Something in fully connected like feed-forward perceptrons you take for granted. You just generate a multiplication and you generate a number and you take mean squared error. Here, generating that sort of equivalent to mean squared error is needs a little more work. Does that make sense? But in reality, what you're trying to say, how I calculate how much error my model made and how I use that to update the parameters of my network. Here, all the efforts are to predict the mean. As I said, we keep the sigma fixed, and we are trying to predict the mean of these Gaussian distributions. We say, okay, if you know we take a sigma, whatever, if you predict the mean, we're just going to deviate around that sigma, right? And we are making sigma fixed to make our computationally more tractable, because we already have a large number of parameters. And in variational autoencoders and in other models, I gave you an example of how big these parameters spaces are. And take like 1000 by 1000 image, if that's, or you even take like 100 by 100 image, which is a tiny image, you have 10,000 just pixels, and for each of them, you're going to learn lots of these parameters. For 1000 step, your parameter space explodes. And in reality, what you're trying to do, let's say if you had 100 by 100, it's again, I'm oversimplifying, you will have more parameters than that. We have 10,000 pixels, and imagine for each 10,000 pixels, you have 1000 steps multiplied by 10,000 multiplied by 1000 steps. You have 10 million sort of just superficial parameters here to learn. And somewhere, a combination of those 10 million will give you the perfect image. The whole effort is varied in the combination of these 10 million variations they can take, and each of them they can take a value. Even let's say between 0 and 1 is a continuous value. They can take any value. You can see it's just is the entire universe can just cover it, and you will have still variations of doing it. And the entire effort is what combination of these parameters will give you a best space. Interestingly, with some effort and some linear algebra, you find this magical steps of actually calculating what loss you can take it and how that you can use that loss in your benefit to drive you towards an optimum point. Not necessarily the best result, but close to the best result. And the better you get in this, you're going to create better quality images. Make sense? Add a little more parameters into it. The loss function will look something like this. This is explaining now something I also struggle. But basically, no, you just add the z's and x's from here to this model, and you will get closer to something like this. And this will become your main loss function. And you will use that loss function in some funny way. It looks like a mini-squared error. It's not, obviously, but this is a sort of standard sort of normal distribution. Comes epsilon from here. And these are for each of the steps. You take the GT, you calculate GT of that, and obviously you mean it across all the steps, and that will become your loss function. The diffusion algorithm, basically what happens is, when it says in the diffusion model, you start with uniform distribution and then the uniform distribution to t steps, and then you start with normal sort of representation. Imagine in your training, you are not really drawing from random sample. In your training, you already have generated that Gaussian representation. In training, you're using your steps 1,000 as your starting point, and you're trying to reverse it back. But once you have trained your network large enough, and your model is complete and trained, now actually the actual unseen data generation starts from absolute random. Condition to text you have learned, and then you calculate the loss and update your your model, and you repeat and repeat until your model converges. By convergence means you are basically stop at some point when your reconstruction loss is at the time you are either happy, or your network more than that starts now fluctuating and becoming worse. Because often if you've trained neural networks, just training them for a long time necessarily is not going to benefit. You have to monitor how it's helping. Yes. GT is basically you plug this z and x into this, and you create a function which represents the entire thing you're taking from it. I haven't shown it here. You're right. I haven't defined where GT is. Go and look at Simon Prince's work, and you will see the definition. I didn't plug it, but I said if you plug these things and do a few more steps, you will end up something like this. In reality, I've eliminated a few steps on the way. Yeah, I haven't shown where you get the GT, but in reality, what you do, you plug this in this formula, and you go, and then you what you get, you just basically encapsulate it as a function called a GT, and then your model will look like this. Yeah, I've skipped a few steps. It's a bit longer. No, makes sense. Makes sense. Just look at Simon Prince. His book is your friend. And the sampling starts, what you do, you just draw your ZT as from a normal distribution of a mu of 0 and the sigma of, this is an identity matrix if you see I. And then from this, you can calculate all the Z thetas using this. And basically, your X will be conditioned to this. Obviously, GT is conditioned to the parameter of the neural network. That's your encoder network. Yeah, it represents your encoder network with certain parameters. Okay, the only requirement for the model that its input and output are dimensionally identical. That's again another thing to Fatima's earlier question. Like in variational autoencoder, obviously you generate your Z dimensions you can control, how many Zs you want, but still what you generate as output is very similar in dimensions, are the same dimensions are your input when you're training your network. Here is the same. If you're using 100 by 100 images, your output is 100 by 100, and you take it from there. The requirements here. The neural networks need to take a noised image and basically predicts the noise. And you can see now the models which work in end-to-end and add more complexities move from different scales to other scales. They are adding some other steps in between. But they are not only using diffusion, they might add other scale. Not first they scale it up and then add it, feed it. It's just what I'm trying to say. The end-to-end models of what you see, you give a cat and generates a cat, it may not be necessarily only a diffusion, could be other steps in between to be able to do that. And the neural network takes basically, again, if you have used PyTorch or TensorFlow, you're familiar with the tensors. Each of your data represents the tensor and gives a tensor of the same diffusion and with the same shape. But in reality, the steps in between are usually created with other networks. What I'm trying to say is you're giving your input image. In reality, your diffusion might work on a different scaled image. And then you again reverse that process. It's not just only you're using a diffusion, you're using a network in between also to take the dimension of your image, do some convolution out of your image, and then also you're going to reverse that. One of the common architectures, or the original Ho and et al., when they wrote the paper, I think they also used UNet. UNet is just the deep neural network architecture, which takes images of, like here, it takes images of certain sort of dimension, and sort of adds multiple convolutional and pooling and different layers. And then you can then reverse that and it regenerates again the image. What you do now, rather than just taking the original image and doing the diffusion, you're adding the diffusion somewhere in between in the unit images. Does that make sense? That also helps with the performance of model and sort of improves the reliability of the models. Then in reality, again, what I'm trying to say, your diffusion just doesn't take exactly at 100 by 100 and applies at 100 by 100, but run it through a convolutional neural network and sort of an architecture like UNet model. Again, if you're interested, this is just a schematic view of how UNet works and different layers in UNet. You can plug this with anything else. You might just take, my 100 by 100 image, I added a fully connected network. I don't know, add whatever you want to add. But obviously that will have an effect of how your diffusion is going to work. The typical architecture they used was a convolutional neural network. And I think in lecture 7, I covered convolutional neural network and how they work. Again, if you're interested, please go and look at our GitHub page. And the reverse project, as I said, you're trying to learn the log likelihood, and you go from the log likelihoods to go across the pixel. Again, what you do, this is not, it's just a simplification of writing the process as a probabilistic model. I've already gone through the linear algebra and saying, but in reality, what you're trying to do, you're saying the condition given x1, you're trying to predict x0, and that's conditioned to all the steps before that, step by step, which again, repeating the same thing as I said. In reality, I showed all this, and I said you keep the sigma fixed and you predict the mu distribution. In reality, the diffusion models, when they generate it, they are looking at one step to the other and just predicting the noise across the image. They just predict the noise. There's practical implementation of it. Exactly, they do the noise prediction. Now you're giving time 1, and you're just trying to predict what noise happened. You're just trying to see what Gaussian noise was applied to take him from one step to the other. You do just noise prediction. One of the things is when you're doing this on images, also you're first what you do, you scale all the RGB images. You scale it to the linearity of 1 minus 1. Basically, you do a Z normalization. You do a Z normalization. That also improves the sort of the process. In reality, if you think you're taking it from, you're adding normal Gaussian noise from a normal distribution, also scaling your pixels to Z normalization will help with that process, especially learning the reverse process. And that shows how you can do it. If you have like your pixels are basically represented by 8 bits, you have to divide it by 255. Obviously, you might have now your pixels have much more resolution, but this is like for an RGB image. if you've done image processing, you're familiar with concepts. Just to scale them to as Z sort of normalization across each channel. By the way, if you have RGB, you do it across each channel. You do that. Again, in training process, the forward process is just straightforward. You take your image and you apply Gaussian noise across like multiple steps. You repeated it many times, and then use those images, and you're trying to calculate the loss. This stands for the loss function, the delta or gradient of the loss. Obviously, I forgot to say, when you calculate the loss, then what you need the gradient of the loss. But like, I'll leave it there. But you know, when you have the loss, it's just not the loss. You take the gradients of the loss. You take the gradient of the loss will look something like this. And you just keep updating your weights. In the sampling part, now once you have trained your model, you just start with noise. This is the model. You have given all the training samples. And here you just say, now this is the trained model. If the trained model ready, you just say, now you just create a random noise, and your model reverses that random noise using these functions. And what happens is generates an X0. And ideally, if you've trained your model really well, that the X0 should look like images you have trained your model for. Like, let's say your entire images were just MRI of healthy brain, and you have given 10,000 images, and you've trained it, I don't know, for 30 epochs. The assumption is now you just tell model, generate a few more, let's see how they look like. And they should look like an MRI of a healthy brain or an AD brain or brain with certain lesion in certain parts. It generates it. Now, if you had multiple classes, goes to Olivia's earlier question, you just conditioned, you add another condition in your training. You're saying this is a brain with lesion in this area, and this starting point would be conditioned to that criteria. It turns out, until very, very recently, until like probably a year or 2 years ago, diffusion models were the benchmark. They were the best models, and still they are. They are one of the most popular ways of generating all this synthetic images, and you come across all these models. And like, if you follow this trend, like a few years ago, before, like all the academic publications, everything was sort of, people were using GANs, generative adversarial networks. These adversarial networks were very, very popular. Suddenly, diffusion came and swept everything and created much more better examples, and really, like, I'm not saying each of them they have their own utility, but I'm saying just suddenly the diffusion models became mind-blowingly really, really good, and the variety they could create was also very interesting. Again, that was a challenge in generative adversarial networks. And until recently, they have been, well, still they are one of the most popular ones. And as I said, like Roxandra is already using like some pre-processing techniques to take EEG to convert it to sort of heat map image representations, which within itself is an interesting sort of task, and then trains a diffusion model to create this. But this work recently came out, and I think I showed this in the variational autoencoders, which uses transformer. And it turns out it's called Muse and came from Google Research. And if you look at their paper, they claim Muse in benchmarks outperforms all the existing models, the diffusion models and everything else in actually the images it generates. And they have a website, and look at, I don't know, probably they have chosen some of the very good examples of it, but the quality of the images they create is just mind-blowing. Again, like everything else, all these things have good and bad utilities. I mean, we had a discussion during the module about the ethics AI and doing responsible machine learning. I'm not going to cover that here. Here, my effort has been providing some insights into actually internal structures of this model. We started looking at the transformers, and I started looking at how transformers can be used for images and natural language processing, but we can use it for behavioral data, for different types of time series data if you formulate it correctly. And briefly, I mentioned it, and I showed this image in transformers. You can also apply them for images. It turns out, if you have a sort of a clever architecture of a transformer, here you're using obviously multiple transformers, and sort of look at the architecture, and if you're interested, read the paper. Actually, the image you're generating can outperform all that complicated model. It means all doesn't matter. You learned all the steps, all the noise and things. there are other ways of doing it. And I'm sure the AI will come up with better and better solutions. At the moment, one of the things all these models struggle is the computational power. They extremely computationally heavy. Like take 1,000 steps, and as I said, just with a simple calculation, you could see how the parameter space is big and how complicated it is that. And in type of things you might be interested here, like taking the brain images, like looking at the effect of different things. Could I condition it to different things? What would have been the effect of these things if I don't stimulate this part of brain? What would have happened in my MRI image? What would have been? These type of things probably in diffusion models are a little much more difficult to control, because I'm hoping by end of today, you've noticed if you add anything to your input data across the different stages, your model might just assume they are noise and eliminate them. And that's one of the biggest challenges now Roxandra is trying to, in her model, trying to address, which I don't know how, but you will magically, I'm sure you're more clever than me, you will find a solution. But you can see in other models like transformers or variational autoencoders, you might have better tools to control that. And I think on that note, I'll stop. And as usual, if you're more interested in the topic, Simon Prince's book is really, really good. There are some good online sources as well on that, and there are plenty of examples. And if I think at some point I had cited the original paper. If you're interested, you can read the original paper, or Simon Prince's book also references the original works on this. Any questions? Any questions online?
Can I ask you a question, Payam?
Sure.
Thank you so much. I've really enjoyed the last few lectures. I had a question about goes back to my original question about when do we use which method. Let's say you have a series of brain scans and you're interested in segmenting a specific abnormality, let's say microbleeds, which are like small 2 millimeter, 3 millimeter spherical lesions that some brains have and some brains don't. And let's say you have some manual segmentations of these. Do you need to use any of the, I mean, it sounds like diffusion model might not be good because you presumably need to identify some of those features, these latent features, let's say something spherical. And so maybe like a variational encoder might be useful, or do you even need to use that? I mean, for just basic segmentation, do you need to go down this route?
I think look at these are obviously generative models. They are designed
Yeah.
in principle to generate synthetic
Yeah.
data. But some of them have also utilities. You can also use them as sort of your feature extraction. For example, if these lesions they have like, or segmentation you want to do has a spatial characteristic, or a part of image has certain characteristic, you might just train a variational autoencoder, give like, let's say hundreds and thousands of these images to say, look, these are the segments I'm interested in, and these are the lesions. And I don't know, you want to train a classifier, whatever, the end sort of end product of it you have in mind, and then your variational autoencoder basically represents that in a lower dimension, which would be easier for you to train a classifier, because you can't give like an MRI image to just a simple classifier to classifier. You need to do some feature extraction. Traditionally, what happens is in image segmentation and things, you did a lot of information engineering. You went and look at, I don't know, gray matters, areas, regions, the edges, and then you started in different voxels, extracted features. One of the things the deep neural network did do, they basically, rather than doing it handcrafted feature engineering, you delegate it to a deep neural network, and the deep neural network takes over and basically find some intrinsic features from this. My feeling is a combination of, in the specific task you said, maybe like a convolutional variational autoencoder could be an interesting way of looking at it. In a different way, Nan, I think, is online. You can have a chat with Nan afterwards. For her PhD, like Nan's PhD research, part of it is looking at, we have this sleep data from our sleep maps from AD patients, and we have from around sort of 2 million nights of control groups. Some of them are the same age group. You can also do age match. And we have this sleep map at every, like per night, gives you per minute heart rate, breathing rate, and gives you like people sleep in and out. You have this data. One of the things Nan has done, for now, take it as a leap of magic, she takes this data and creates images. like every patient's, let's say 1 week of sleep becomes a heat map of an image. Then you have this bunch of images. When you do this, now the task becomes very similar to any other image processing task. What you're going to do, you're trying to look at, can I create a classifier looking at this heat map images? When I say heat map, I'm oversimplifying Nan's entire work, but on that pre-processing part. But say these are heat map of images. You want to say, can I extract certain features? Can I feed it to a classifier to say this is an AD sleep pattern, this is an MCI sleep pattern, this is an healthy sleep pattern. In that sense, what Nan does is applies a convolutional network first, which looks at lots of convolutional filters and does some sampling in that, and then takes the results of the convolutional layers, feeds it to a variational autoencoder, and then generates the Z samples, and then reconstructs that image again. The model just learns to reconstruct it. Becomes just a variational, convolutional variational autoencoder, which just a sort of supervised model, and auto-regressive model just learns to do this. Once we have trained the encoder decoder, in reality, in our specific task, we are not interested in the decoder. We just put the decoder aside and we keep the encoder. Now, what we do, we have now specific samples. We know this is like an AD brain, and we feed it and we train a classifier. Now the classifier is very sort of works on a feature space and can create better you can create better generalizability in the model. In that sense, we have repurposed the generative model to give us a feature representation, which also keeps the sort of spatial correlations in this. In the same way, if you're interested in like sort of temporal order in this and a spatial temporal order, in our images, for example, for heat map for sleep, we are adding the temporal order into the images. But imagine if you just wanted to give the temporal order separately, you might just use a transformer sort of autoencoder, which use a transformer to extract latent spaces, and then you add the temporal dimension. This is sort of repurposing that, and there is nothing wrong with it towards the purpose you are looking for.
By temporal order in this specific example, do you mean, let's say, scans at different times? Is that what you mean?
When I said temporal order, for example, in sleep, temporal order of sleep of
okay.
tonight, and
yeah,
the MRI scans probably is, unless you do like you have different scans, and different scans contribute to the prediction, which often is not the case you're looking for.
Yeah.
On this.
Great, thank you. Thanks.
Any other questions? Okay. Thank you very much. I hope you found this useful. For the people who attended the module, I feel I've covered more than actually again, as I said, if you would have done a computer science degree or module. But there are two still important things in deep neural network and generally in the machine learning trends I haven't covered. And one is the graphical models and graph neural networks, and one is energy-based models. There are also some new trends in machine learning. They use ideas from particle physics, and they use energy-based models. And there are some energy-based models, categories of 4 generative models as well. If you were interested in this, and depending on my time, I'll be happy to cover it. Probably I'm busy until mid-June, but it will be later in June. And on July, I'm mostly away traveling for conferences and things, but could be after mid-June and until end of June. I'm happy to do that. If you were interested, email Deborah or email me, and then Deborah and I will look at to see how many people are interested in, and we make a decision. Thank you very much, and enjoy your weekend. And I'll put the recording online. Thanks very much.